last lecture we were discussing about series impedance of distribution lines and feeders. We have seen that if the lines are transposed, the impedances of all the three phases they are equal and they can be easily calculated. We have discussed those formulae in the last class. We also discussed if the lines are untransposed, then it will be matrix of 3 by 3 size. So, series impedance of the distribution line will be represented using 3 by 3 size impedance matrix. And then at the end of the lecture we were discussing about if there are unbalanced ground current which are flowing through the ground, and we have seen that these currents affect the series impedance of the line. And in the last class basically we have seen that how they affect. So, in this case if you remember, in the last class we have discussed about this circuit here, and in this circuit we have considered two conductors. This is conductor I and this is conductor J, and there are currents which are flowing II and IJ, and unbalanced current means II minus IJ will be flowing through the ground, or you can say II plus IJ which will be flowing through the ground. Now, because of this current, the self impedance of the conductor I as well as conductor J will get modified, as well as mutual impedances between the conductors they will get modified. And in the last class we have derived those modified expressions of impedances. Those are ZII cap and ZIJ cap. So, mutual impedance of between I and J will get modified like this, and self impedance of the conductor I will get modified like this. And if you see this equation here, we have seen that this Ri is nothing but resistance of the conductor which is available to us from the data sheet. This term which is natural log of 1 divided by GMRI, which is depend upon your GMR of the conductor I, which can be easily estimated. However, if you observe these two terms, one is Rd which is resistance of your ground path, and this another term natural log of dId multiplied by ddi divided by GMRd. So, this is nothing but GMR of your ground conductor. This is nothing but distance between conductor I to the ground conductor, and this is nothing but distance between again conductor I to the ground conductor. And we have seen that when these currents flow through the ground, we are not having definite path for these particular currents, and because of that it is very difficult to get all these distances as well as GMRs of ground conductors. Now, when these ground currents are flowing, as we have seen that there will be mutual impedance between ground current to the conductor J, which is represented by ZD. There will be mutual impedance between ground current and I conductor, which will be represented by ZID, and there will be self impedance of ground path which will be given by ZDD, where this is resistive part which is RD. So, getting this RD as well as all these distances of ground conductor is tricky thing. Also, if you see in mutual impedance part, there is RD term here, again it is difficult to get. Similarly, we are getting this term here which is depend on the distances with respect to ground conductor as well as GMR of your ground conductor. However, this distance is available, so we can get this term. So, this term is not available, this term is not available, this term is not available, and this term, these four terms are not available. Anyway, these two terms are okay, this term is not available. So, I will just erase this, this is available. So, RD is not available here. So, this is because, as I explained you, the earth is consisting of many layers of you can say they can be represented by various types of conductor. You can say that top layer will be represented by small conductor layer, then there will be some bigger conductors at below that, and then there will be conductor size will go on increasing as you go inside your earth surface. And this earth surface is easily considered using your Carson's equations. So, as we discussed, since a distribution feeder is inherently unbalanced, so many times your ground path will be having currents flowing through it, and because of that your self as well as mutual impedances will get altered. Then we have seen the earth is conductor of enormous dimension and non-uniform conductivity. The earth current distribution is not uniform. So, when the currents are flowing to the earth surface, they will be non-uniform. Therefore, it becomes very difficult to calculate the impedance of the conductor with earth return, because for that we need to know the distribution of current returning to the earth, and which is not available because your earth is very non-uniform resistivity, and because of that earth currents will not get uniformly distributed. So, getting the impedance with earth returns is quite a difficult thing. However, this problem is attacked by many engineers, and they have made many assumptions while deriving that. One of them is very famous, which is derived by Carson in 1926, and this is applicable to power system study, which will give us the self and mutual impedances of any arbitrary number of conductors when there is earth return current flowing. However, actual Carson's equations, they consist of infinite series, which will be difficult to calculate. So, in due course of the time, many people have modified these equations so that we can easily use them for power system studies or distribution system studies. So, for that, one of the modifications to the Carson's equation is using equivalent depth of earth return. So, using equivalent depth of earth return, the Carson's equations are modified. So, in this case, what they do, if there are two conductors, say this is conductor 1 and this is conductor 2 at say some height h1 and h2, and to calculate the inductance we consider images of those conductor. So, image of conductor 1 is this one, image of conductor 2 is this one. However, we are not considering these images at exactly h1 distance below the ground. However, we consider these images at distance d from the earth's surface, or we can say distance between the two conductor, we consider them as a distance d, and this distance is called as equivalent depth of earth return. And using this equivalent depth of earth return, we can modify our Carson's equations. And here this equivalent depth of earth return is given by this formula here, which is 2160 in the square root. This is nothing but resistivity of earth, and this is nothing but your frequency of operation. So, if the frequency increases, your equivalent depth of earth return goes down. This formula is given in unit as a feet. However, many times we use meter as a unit to measure distance between the conductors. So, in that case, this formula can be converted into meters by multiplying this conversion factor, which is converting meters feet to meter. Now, let us see what are these modified equations. So, modified equations given by Carson's are shown here. So, this gives us self impedance of the conductor, and this gives us mutual impedance between the conductors. And if you compare these equations with our equations which we have derived in case of if there are earth currents, so we can see that this term was not available to us, as well as these two terms were not available to us. And Carson has given these two terms in terms of frequency. So, this R d is represented by this term here, that is 9.86 into 10 raised to minus 7 multiplied by frequency of operation, and this natural log multiplied by these distances and GMRs can be represented by equivalent depth of earth return. So, we can replace this whole natural log term in using natural log of d here. Similarly, this term can be also replaced using natural log of d. So, we have got the required quantities which were unknown to us, and those are given by natural log of d, and this R d term is given by this 9.86 into 10 raised to minus 7 into frequency. And as we discussed, your equivalent depth of earth return, which is d, is given by this expression. Now, let us see how we can get this equation for 50 hertz, and if your unit of measurement of transmission line length is in kilometer. So, 50 hertz is your operating frequency of your distribution system, and lengths of feeder we are giving in kilometers. One more thing we are considering it here, that is conductor distances, means distance between the conductors, we are considering in meters. So, in that case, the formulae which are given by Carson's, or expression given by Carson's, can be modified like this. So, in this case, this is your Carson's equation for self impedance, and in this case this term will get modified. We can put the frequency is equal to 50 hertz. So, instead of frequency I put 50 hertz here. Also this omega will get modified, and this omega will become 2 pi into 50. Now, if you multiply this term by 1000 here, because here we are taking 1000, because we are considering this formula was in ohms per meter, and if you want to convert into ohms per kilometer, we need to multiply it by 1000. So, this term here multiplied by 1000 will get this term here, and this term here multiplied by 1000 will get this term here. So, the formula for self impedance is given by this expression here. I can say this is 1, and the formula for mutual impedance is given by this here. So, this again it is in ohms per meter. So, we need to multiply it by 1000 to get ohms per kilometer. So, we need to multiply this expression by 1000, and then we need to put this frequency is equal to 50 hertz, and here also it will be 2 pi into 50, and so if you put these values, I will get expression for mutual impedance. So, this is expression 2, this is expression for self impedance, and this is expression for mutual impedance. When the frequency is 50 hertz and your distance is in kilometer, and distance between the conductor, distances between the conductor if they are given in meters. And in this case, this d is calculated using this formula here. So, d is 2160 into resistivity divided by frequency and square root of it. This formula is in feet, but here we are considering distances in meter. So, we need to convert this formula into meters. So, this is your feet to meter conversion. And resistivity of earth, so depending upon type of earth, your resistivity of the earth will change. So, here for damp earth resistivity is 100, for dry earth it is around 1000, and for sea water it is around 1. So, depending upon the area where your distribution system is existing, you can choose your resistivity of earth, you can put it here. So, this in this particular formula I have considered damp earth, which is a general case. So, I put the resistivity of damp earth here, frequency is 50 hertz, and then you can get the equivalent depth of earth return, and if I take the natural log of it, I will get this term here. So, this is how we get modified Carson's equations of self impedance and mutual impedance. Let us say unit of your system or frequency is in 60 hertz, or frequency of your distribution system is 60 hertz. Units of measurement of distances of the feeder is in miles, and your distances between the conductors, if they are given in feet. Then we can easily modify these expressions for self impedance and mutual impedance by putting 50 hertz 60 hertz frequency here, and here also this will become 2 pi into 60. So, here this is 2 pi into 60 and this f will be replaced by 60, and here this meter need to be converted into miles. So, this conversion factor is 1609.34 mile, number of meters in mile, and if you simplify this using this, I will get this expression here, which gives me self impedance of the conductor at 60 hertz and mile as a unit. So, ohm per mile. Similarly, the mutual impedance between the conductor will be calculated by putting frequency in these two terms and multiplying it by 1609.34 to convert into miles. So, I will get this expression here, which will give me mutual impedance between the conductor. In this case, since distances are considered in feet, those are distances between the conductors. So, in that case you can use directly this formula here, and I can put the resistivity of damp earth, which will give me d, and this d I put into this expression to get this term here. So, here when you are using this formula, this GMR should be in feet as well as the distance dij should be in feet, because your d we are considering in feet. So, whenever we are considering d in feet, you have to use dij distance in feet itself. So, this is how we can get the expressions for self and mutual impedances of distribution lines at 60 hertz and mile unit. So, if you see the summary of these impedances of distribution line, so you have seen that in case of transposed line, the impedances of all the three phases they are same. So, in this case ZA is equal to ZB is equal to ZC, they will be given by this expression here, and which will be having only one term. However, if the line is untransposed, but the ground currents if you are not considering, then your expression is in terms of matrix here, which will give me matrix of 3 by 3 size, and which will be consisting of all the impedances and all these impedances will be calculated using these self and mutual impedance formula. So, diagonal entries of this matrix will be calculated using this expression here, and non-diagonal entries will be calculated using this expression. Then just now we have derived the expressions for self and mutual impedances if the line is untransposed and if there are ground return current present. So, we have seen that the impedances will get altered because of these ground currents, and basically it is because of mutual coupling between ground currents and your phase conductors. These impedances are getting altered, and in that case if there is ground return current present, your expression for self impedance is given by this, which is in ohms per kilometer, where the distances of GMRI and Dij they are taken in terms of meters, and this is your expression for mutual impedance. Now, let us see how we can use this to get the what is called as primitive impedance matrix of your transmission or distribution line. So, let us consider this simple distribution line. There are 3 phases A, B, C, and there is one neutral conductor N. I have mentioned all the distances between all the conductor, as well as I have mentioned the height of conductor with respect to ground. And using the expressions which we have derived, we can get this primitive impedance matrix. The size of primitive impedance matrix will be number of conductors by number of conductors. If there are n number of conductors in your system, so size of primitive impedance matrix will be always n by n. So, in this case there are 4 conductors, means size of primitive impedance matrix will be 4 by 4, and entries of this 4 by 4 primitive impedance matrix will be calculated using these expressions of self impedance which you have derived just now and mutual impedance. And if you see here what we need resistance per kilometer of the conductor, GMR of that conductor, and distance between conductors to get the mutual impedance. So, we generally know these things from the design of your distribution line as well as data sheets of the conductor, and using these values we can get this primitive impedance matrix using this formula. So, you can use this self impedance formula here to get the diagonal entries of this primitive impedance matrix. Those are ZAA, ZBB, ZCC and ZNN. N is actually your neutral conductor here, and off diagonal entries of this matrix. So, basically all these entries we can get it from this expression 2. Again this is symmetric matrix. So, the entries of lower triangular half of this matrix can be easily calculated, or directly we can take it from upper triangular part of the matrix. Then we are going to divide this matrix into 4 parts. The parts corresponding to phase conductors we want to separate from parts corresponding to neutral conductors. So, if you see, this part of the matrix is having only the phase conductors, and this is actually represented by Zij. So, this part of the matrix I am representing it by Zij. So, where Ij I am considering corresponding to your phase conductors. This part which consisting of Zin, so this I am representing by Zin because it is between impedances between your phase conductors and neutral conductors which we want to separate out. Here also this part, if you see, this consists of phase conductors as well as neutral conductors. So, I am representing by Znj, and this part is only the neutral conductor part. So, this is represented by Zn. So, if you write these 4 parts in short form, I will get expression like this. Again, let us see for bigger matrix, if there are 3 phase conductors and 3 neutral or earth conductors, in that case you will be having, say, this L, M, N. So, A, B, C I am considering phase conductors, and L, M, N are your ground or neutral conductors. So, in this case again we can divide this part is consisting of only terms related to phase conductors. So, this will be represented by Zij. This is representing your phase as well as neutral conductors. So, this will be represented by Zin. This is again representing phase as well as neutral conductors. So, this will be Znj, and this is representing only the neutral conductor. So, this is Znn. This is how we can divide this matrix into 4 parts. Now, let us see what is the meaning of these 4 parts. So, here I have shown one typical case where there are 3 phase conductors and one neutral conductor, and this neutral conductor is having multi ground system. So, it is this neutral conductor is grounded at various location along its path. So, here it is grounded as well as here it is grounded. So, this system of equations we can write it like this. So, voltages at this terminal of all the three conductors with respect to ground. So, VAG with this voltage, VBG and VCG and VNG, all the three all the four conductor voltages will be represented like this. They will be voltages of these conductors at these terminal plus the drop which is happening in this part of the feeder. So, in this case, so the voltages at the secondary end, they are represented by a dash term here. So, V dash AG, V dash BG, V dash CG and V dash NG, they are the receiving end voltages plus the drop along the feeder will be represented by this term here. And this system of equations, so these three terms I can write in short form as VABC, this term as it is VNG here. These three terms I can write in short form as V dash ABC, this term here, and this term is V dash NG as it is. These three currents which are basically phase currents I can write using IABC notation, and this is your neutral current which is IN notation here. Therefore, this matrix will get again divided into 4 parts similar to those. So, this is corresponding to your phase conductors and the remaining parts are phase conductor to neutral conductor and only the neutral conductor part. So, again this matrix is divided into 4 parts and these are the 4 parts. So, this part is only related to your phase conductors, this is phase and neutral, this is again phase and neutral, and this part is only related to your neutral conductor. So, therefore, this equation from this slide I can take it on next slide. So, if you see this equation here, what I can do, I can write this equation number 1 say into form of 2 equations. So, this is your first equation which is first row of this, and second equation is which is second row, I can write them separately. So, VABC will be equal to V dash ABC plus Zij into IABC plus Zi into IN. So, this is your first equation here, first row, and the second equation corresponding to second row is VNG which will be equal to V dash NG plus your ZNJ into IABC plus ZNN into IN. So, this is your second equation. I can say third equation, this is your second equation. Now, if you observe this VNG and V dash NG term here. So, if you go to the previous slide and if you observe here, as I told you, this NG and this and V dash NG. So, VNG and V dash NG, since they are grounded it at multiple location, the voltages VNG and V dash NG, they will be 0. So, you can see that this VNG voltage and V dash NG, because of multiple grounding, they will be 0. So, from this equation number 3, so from this equation number 3 I can write VNG which is 0, V dash NG is 0, and then the remaining terms are ZNJ multiplied by IABC and ZNN multiplied by IN. And then this expression I can write in terms of IN by taking other terms on left hand side. So, I can write IN will be equal to this term here which is minus ZNN inverse multiplied by ZNJ into IABC. Then we can put this into expression 2 here. So, if you put this value into expression 2, so this term will get replaced by this term here. So, after replacing that in with this term here, I will get this term here. And in this case, I can take this IABC common out. So, the overall term in the bracket will be Zij plus this term here, which is Zin multiplied by Zn inverse multiplied by Znj, and this bracketed term I am calling ZABC, and on this side it is VABC and V dash ABC, ZABC and IABC. So, if you observe this expression here, which consists of only phase related voltages and phase or line currents only. So, nowhere there is terms related to neutral conductor voltages or neutral conductor currents. So, we have eliminated your neutral conductor using this expression here, where your ZABC is represented by this term. So, basically ZABC is given by this term by separating your primitive impedance matrix into 4 parts. So, this is called as Cron reduction, where we are eliminating the ground as well as neutral conductors. So, basically what we did, the system which is having 4 conductors, we have converted that system into only 3 phase conductors by eliminating your ground conductor here. So, this, but it is just directly not eliminated. However, we have taken the effect of those conductor currents on the phase conductor by doing Cron reduction. And using the Cron reduction, we have seen that your 4 by 4 primitive impedance matrix. So, this was your primitive impedance matrix, which is basically conductor size by conductor size. So, in this case it is 4 by 4 because we are considering 4 conductors here. We have divided into 4 parts, and using Cron reduction, which is given by this expression here, we have got your phase impedance matrix. So, this is called as phase impedance matrix, which will be number of phases by number of phases. Generally there are 3 phases, so it will be 3 by 3 in size. So, primitive impedance matrix, which was 4 by 4 in size, we have converted them into 3 by 3 size using Cron reduction. So, let us take one example with actual dimensions. So, here we have seen there are 4 conductors, and for these 4 conductors you are having this primitive impedance matrix, whose entries will be calculated using these expressions of self and mutual impedances, and we have discussed that these diagonal entries of this matrix will be calculated using self impedance formula, which is formula number 1, and the off diagonal entries will be calculated using this mutual impedance formula. And we have seen that it only needs your resistance per kilometer of your feeder conductor and your GMR of conductor. And to get the mutual impedance, we need distances between the 2 conductor, for which we are interested in calculating mutual impedance. And once you get primitive impedance matrix, using this you have to do the Cron reduction to get phase impedance matrix, which is 3 by 3 in size. So, in this example I have considered these distances, and GMRs and resistance per kilometer required will be taken from the data sheets, because we know which conductors we have used for this system. So, for phase conductors we have used this 336, 400, which is having 26 by 7, means 26 aluminum conductor and 7 steel conductor. So, it is ACSR conductor here, and for neutral conductor we have used this 4 by 0, which is having 4 by 1 ACSR, means there are 6 aluminum strands and 1 steel strand. So, for these two conductors, from the data sheets we can get GMRs of those conductors. So, GMR of phase conductor is given by this, and GMR of neutral conductor is this. Resistance of phase conductor per kilometer, and this is your resistance of neutral conductor per kilometer. So, basically these two things are required in Carson's equations, and you can easily get the distances between various conductors. So, DAB 0.76 meter, DBC 1.37 meter, DCA 2.13 meter, DAN 1.72 meter, DBN 1.3 meter, and DCN 1.52 meter. You can easily calculate them from the design sheet of your distribution line, and once you get those distances and GMRs of the conductor, you can get the self impedance of say conductor A that can be calculated using this self impedance formula here. Resistance, we can take it from resistance of the phase conductor A, and GMR of conductor A will be taken from GMR of the phase conductor, and if you put these values into this expression, I will get ZAA impedance, which is having this value here, which is ohm per kilometer. Similarly, we can get mutual impedance between A and B conductor. So, mutual impedance between these two conductors, again we are using this mutual impedance formula given by Carson, and in this case we need distance between the two conductor DAB, which is 0.762 meter, and DAB I am putting it here, and after putting DAB I will get this mutual impedance between conductor A and B. Similarly, we can get the mutual impedances as well as self impedances of all the conductors and mutual impedances between all the pairs of the conductors, and if you do this I will get this primitive impedance matrix, which is 4 by 4 because we are using 4 conductors in this system. So, this is your primitive impedance matrix, which is 4 by 4 size calculated using these self and mutual impedance formulae given by Carson. So, after getting primitive impedance matrix, we need to use Cron reduction technique to get the phase impedance matrix. So, we need to divide this primitive impedance matrix into 4 parts, separating phase conductors and neutral conductors. So, in this case these are related to phase conductors and this is neutral conductors. Similarly, these rows are corresponding to phase conductors. See, and this is neutral conductor. So, this is nothing but matrix which is related to only the phase conductor, which is represented by Zij. This is related to neutral and phase conductors. So, this is Zin here. This is again related to phase and neutral conductors. So, this is Znj here, and this is related to only neutral conductors. So, this is your Znn. So, from these 4 parts and using the expression of the Cron's reduction which you have obtained. So, these are the 4 parts into we can put into this Cron reduction equation, and if you do that I will get the phase impedance matrix which is given by this. So, this is how we can get the series impedance matrix of your distribution line or feeder. So, in summary of today's lecture, we have seen calculation of series impedance of distribution lines and feeders. Specifically, we have seen this calculation for the systems which consisting of earth return current. So, if there are earth return current, we have seen that we can use Carson's equations, and we have derived these Carson's equations and the modified form of Carson's equation, and we have seen that it can be used to calculate the impedances of the distribution line with earth return. And then we have seen Cron reduction. Basically, this Cron reduction converts your primitive impedance matrix to the phase impedance matrix. Primitive impedance matrix we have seen, it is number of conductor by number of conductor size, which convert into phase impedance matrix, which is 3 by 3 in size. And finally, we have taken one typical example of distribution feeder, and for that feeder we have calculated primitive impedance matrix, and then we have converted that primitive impedance matrix into phase impedance matrix. Thank you.